Now the next test is what we call the limit comparison test. Okay, so the idea is that just like when we saw sequences that are asymptotically equivalent, this means that when they are close to infinity, or when the index is very large, both sequences have very similar terms. So that means that if you sum them, you will get similar values. So the idea is that if you have two sequences that are asymptotically equivalent, then if one is convergent, then the other will be convergent, and the other way around. Okay, so sorry, if one is convergent, then the other is convergent, and if one is divergent, then the other is divergent. Okay, so the convergence, if two sequences are asymptotically equivalent, then the series associated with them, okay, remember it's not the same, the series and the sequence, the series associated with these sequences will have the same convergence. Okay, now if a sub n is negligible in comparison with b sub n, the series associated with b sub n being convergent implies that the series associated with a sub n is also convergent. And you can see this is kind of similar to the to the comparison test, which this means that the terms of a sub n go to 0 much faster than the terms of b sub n do, right? And the other way around. So if the series associated with a sub n is divergent, then this means that the series associated with b sub n is also divergent, especially because if the terms that go, if a sub n go to 0 very, very fast, much faster than b sub n, which means that at some point the terms of b sub n are much larger than the terms of a sub n. Well, if this sum goes to infinity, then it's reasonable to think that this also goes to infinity. Okay, so this is what this is saying. This is similar to the to the comparison test. It's just that you don't need to make sure that every term is greater than the other one. Okay, so some example of this, we have this series. Okay, sum from n equals 1 to infinity of 1 over the square root of 3n squared plus 2n plus 7, right? Well, you could say, well, the square root of 3n squared plus 2n plus 7 is, we know it's asymptotically equivalent to 3n squared, because these terms are negligible in comparison with this, right? And this is exactly the same as square root of 3 times n. Okay, so then the series from n equals 1 to infinity of 1 over the square root of 3 times n, which is none other than this, 1 over the square root of 3 times the series from n equals 1 to 1 over n. This is just the harmonic series, okay? And we know this is divergent, okay? This is non-convergent. But because these two sequences are asymptotically equivalent, you could say, and then this sequence is also going to be divergent. Okay, so that's the idea behind this test. Okay, so as an exercise, prove using appropriately the limit comparison test that we have just seen, that if a sub n is greater than 0 for all n, then, and we know that this is true, that the limit when n goes to infinity of n to the alpha times a sub n is L, so it's a real number that's greater than 0. So this sequence, okay, this sequence is convergent, then the series of a sub n is convergent if alpha is greater than 1, and it's divergent if alpha is smaller or equal than 1. Okay, so just it won't take you long. Just using the limit comparison test, you think a bit about this and about the examples that we have seen about the Riemann series, and then you will have a result. Okay, and finally, the last two tests that we will see. The first one is what they call the root test. Okay, so then again, a sub n is greater than 0, so this is a sequence of non-negative terms, and the limit of the nth root of this sequence is L. Okay, so this is, we haven't gotten to the series yet. Okay, we have a sequence of terms. The nth root, the limit of the nth root of a sub n is L. It's a positive number, right? Then this means that the the series of A sub n is convergent if L is smaller than 1, and it will be divergent if L is greater than 1. And the case L equals 1 remains undecided. Okay? And so what's the idea behind this? This is using the limit comparison test. If this is true, okay, the limit of this is true, then we can say the limit when n goes to infinity of a sub n, the nth root of a sub n divided by L, okay, is 1, right? Because we are dividing both expressions by L, sorry. So we could say that the nth root of a sub n is asymptotically equivalent to L, right? But this can also be written like a sub n is asymptotically equivalent to L to the n, right? So that means that this series, the convergence of this series, a sub n, is the same of this series n equals 1 to infinity of L to the n, right? And this is the geometric series. We know that this is convergent if L is smaller than 1, okay? And if L is greater than 1, then this will be divergent, okay? Let me write it here. N equals 1 to infinity. This will be divergent if L is greater than 1. And if L is equal to 1, then we need to study each case separately, okay? And use the definition, but we will do exercises and you will see what I mean by this, okay? And finally, the quotient test, okay? So from the root test, we can apply one of the corollaries of Stolz theorem that we saw in last unit and see that the condition that the limit when n goes to infinity of the nth root of a sub n equals L implies that the limit, sorry, not that implies that, but this, if this limit a sub n over a sub n minus 1 equals L, then this implies this, and then we have the proof for the root test, okay? So if this is true, then we know this is true as well from the corollary from Stolz theorem, okay? And so just like before, the convergence of this series will depend on the value of L. If L is smaller than 1, then the series will be convergent. If L is greater than 1, the series will be divergent, okay? So keep in mind these two tests. We will use them a lot during the exercises, okay? Okay, so that's it for this video.